So we have discussed about this circuit, this structure last time, and we have a single pole double through switch, and the Vx is a PWM waveform, and by passing this ideal low pass filter, then you can get the BO, that is a DC voltage. And in fact, the Vx include this component. If you, for example, perform the Fourier transform, fast Fourier transform with this, then you can get this kinds of diagram here. Here the zero is what DC component. That is the average value. And what about the omega s? That is the switching frequency. And what about 2 omega s? That's in double over switching frequency and triple switching frequency. So you have the multiple times of the switching frequency component as like this. And here, this expression can be simply modeled as like that here. Bx, that is the time domain function. And here C0 is the average waveform. That is the voltage you want, right? Then the rest of them, this term models the harmonics. I mean the switching frequencies harmonics. So our main purpose is to eliminate this component with what? A low pass filter. So the BO, if you can eliminate this harmonics, then you can get a pure DC signal CO. Then in that case, your output BO is what? Simply the modeled as dVs. Vs is the source voltage and D is the duty. Then let's consider this circuit. This is a simple buck converter, and your single pole double through switch is implemented with this combination. That here you just use a simple MOSFET, but in fact you can also use IGBT as well here. And this is a simple diode. In switching application, your diode performance should be very, very good. I mean, if you should apply, for example, a Schottky diode or fast recovery diode. If you just use very slow recovery diode or a general purpose diode, then eventually your entire power stage will generate the heat because of the reverse recovery energy. So this is a very important component in real application. And what about the LC filter? Yeah, here we just simply modeled as ideal L and ideal C. But in fact, you have a parasitic resistance component here. Then let's simply calculate the filter transfer function like this. So its input is Vx. Vx is a switched waveform. And what about the VO? VO is a filtered waveform. Then if you calculate, obtain the transfer function, then you can simplify as like this. This is a simple LCR circuit, and here C and R are parallel, and also C and R are parallel as like this. Then by calculating this equation, then you can simplify the equation as like this. So here omega 0 is the pole frequency or cutoff frequency. And what about Q? In your textbook, the Q is called the damping ratio, but in fact, it is some opposite meaning. I mean, the Q is just a quality factor. So your damping ratio, original definition is what? That is your original definition of damping ratio. That is zeta, right? The Q is in fact quality factor. So in this lecture, I will just call the value as Q or Q factor, okay? Then, since that is a second order low pass filter, then you have like this kinds of body flood here. So its slope is minus 40 dB per decade. Then this area is what 0 hertz, that is the DC signal. So in that case, your output is just 0 dB. It means your absolute value is 1, right? So this is a switched waveform, and this is a much filtered waveform. And BX, switched waveform, is modeled as like this. And what about BO? In ideal case, this component should be gone. But in practice, still you have the component, but with much reduced value, right? Then its shape are similar, but Cn is changed as a Cn dash, and pi n is changed as pi n dash. What does it mean? Because of your low-pass filter, Cn component has been reduced. Like this. What about the phase? Phase is also changed. So this model, this equation is to model the reduced effect by passing the low pass filter. Okay? So your Cn dash is simply calculated as 10 minus Fourier log and omega s over omega o over 20. Like that. This magnitude is this magnitude. Right? So by increasing the switching frequency, okay, so at the switching frequency, n is just selected as 1. And double over the switching frequency, n is selected as 2. Okay? Then let's simply apply the equations to this example. In this example, your source is 16 volt, and you have the LC filter, and L is 40 microhenry, and C is 470 microfarad, and your output voltage is applied to the 1 ohm load here. Then 20 microsecond of the switching frequency. And what is the switching? This is the switching period. And then what is the switching frequency in this case? 50K, right? 50K hertz is the switching frequency. So omega O, that is the pole frequency, is simply obtained as like this. But that is expressed as radian per second. So if you want to get the hertz, then you should apply 1 over 2 pi to this value. Omega S, that is the switching frequency. Here also, it is expressed in the radian per second. Then what about D? D is the duty ratio. And T on here is 5 microsecond. And Ts is 20 microsecond, right? Then D is 0.25. Then what would be the output voltage here? Your source voltage is 16 and your duty ratio is 0.25. Then what is output voltage? Just 4, right? So if you analyze your output voltage, it could be like this. Okay, 4 is the average value, but near this 4 voltage, then you have this voltage ripple, right? So let's calculate the ripple component. How can you do that? Here, these harmonic components are calculated as like this. First, what about the C1? C1 previously C1 is calculated as like this. Then C1 dash is what? C1 multiply this equation, right? Then by solving this equation, then you can get 3.88 millivolt. 3.88 millivolt. But that is just part. So if you want to get the voltage ripple, then you should apply factor 2 here. Then finally you could get 7.76 millivolt. That is the voltage ripple. Okay? All right. So now you're gonna simulate this model, okay? You make this, build this model in PSIM and simulate it. Okay, so let's consider some filter configuration and their ripple attenuation. We have 3 types of filter here. So we have the SPDT switch, so all of them are based on buck converter. And here you have a load, 1 ohm, 1 ohm. But you have here, the first order filter only contain a single inductor. And the second order filter is a LC filter. And what about the two-stage filter? Two-stage filter contains 2 LC filters. So this is the first order, this is second order. But what about this? This is fourth order. In terms of ripple attenuation, this is the best. But it requires more components. And what about this? If you simply equip this single inductor, then your output voltage cannot be regulated. I mean, it contains also harmonic component. So for the current control application, you can simply apply this single inductor. But if your target is obtain the output voltage, then you cannot apply this circuit. So, for example, the battery charger. In that case, you can apply this because your battery voltage is what? That is not controlled, right? If you, in fact, controlled, but in many cases, your battery itself is already very big capacitor. Battery itself is very big capacitor. So, in battery charger, you don't use this kind of strategy. Then what about the power supply? Power supply application, you can go with this or this. But this circuit is much, much preferred compared to this because of the number of the components. So, this frequency response compare the filter transfer function among these 3 types of filter. Here, the first order filter is high frequency attenuation performance is worst compared to other cases. And what about the second order filter? It includes what? Minus 40 dB per decade. Then what about the two-stage filter? Until this point, it keeps the minus 40 dB per decade, but once you pass this point, then now it is what? Minus 80 dB per decade. So the high frequency, very, very high frequency attenuation performance is the best here. So if you see these first order filters, I mean the output voltage with the first order filter, then its output voltage is like this. Why? You have only resistive load, and the current passed through this resistor is the current passed through this inductor. And your output voltage is just simply the current with the ripple multiply this 1 ohm resistance, right? So this voltage is the shape is exactly same with your current. And okay, this is the second order filter. Still, the peak to peak is about what 0.5 millivolt. That is very, very small value. But if you see the two-stage filter is much, much less than the second order filter. Then let's discuss about the piecewise linear analysis. Okay, the piecewise linear analysis technique is very, very popularly used in the circuit analysis. And here you have a simple buck converter, and this circuit has 2 status, right? First, when the switch is turned on, and second, the switch is turned off. So the piecewise linear analysis is the technique that you just the separate the circuit in case by case. Then finally you just sum the results. Then you can get the circuit a steady state operation. So here the piecewise linear analysis considers the converter as a combination of two linear circuits, the on-time and the off-time sub-circuits. And the operation of the converter is analyzed by examining each circuit individually, and later accounting the behaviors of the two sub-circuits collectively. Then, think about it. You know the linear time invariant circuit, right? Then what about the power electronic circuit? First, is it linear? Mostly it is non-linear, right? And what about time invariant? Time variant or time invariant? Power electronic circuit itself. Think about it. Your switch is always on off. Then, according to your duty ratio, the circuit is continuously changing. Then you can say that is time variant system, right? So, in your undergraduate course, most of your undergraduate course deal with linear time invariant system. But in reality, the power electronic circuit itself is what? Nonlinear time variant circuit. So its analysis is very, very difficult. So that's why we introduce this kind of some techniques. Okay. Then let's see the startup response of a buck converter. When the switch is turned on, the source voltage is connected to the input of the LC filter. When the switch is turned off, the source is separated from the circuit, right? Then, in on-time sub-circuit, your energy is transferred from source to the inductor, so your inductor current increase. It's like this. And if you turn off the circuit, turn off the switch, then your inductor energy is what? Also the freewheeling and also the supplied energy to the load and capacitor. So your inductor energy is what? Reduced. Current is reduced. And again, this operation is continuously repeated. And at the steady state, you know the concept volt-second balance, right? The volt-second balance is per field. Then your amount of increase and decrease are the same. Then, what about this circuit? Here, still your duty ratio is 0.25. Then your input is 16 volt. Then your output voltage is what? 4 volt, right? 4 volt. Then, your output resistance is 0.1 ohm. And here you have 4 volts. Then what is the output current? Average value is 40 ampere, right? 40 ampere. And can you say IL, this bar, means average? Can you say IL, average IL is the same with IO? How come? How come? Think about it. At the steady state, the current pass through, the average capacitor current should be zero, right? Because it's, the input current and output current amount should be the same to fulfill the amp second balance, right? Then the the average value is zero. This average value is 40 ampere. Then average value of this inductor should be also 40 ampere, right? So this is the inductor current, and at the steady state, its average is 40 ampere. So to analyze a buck converter in steady state, then you can follow this process. First, you just perform the piecewise linear analysis, and the operation of the converter is analyzed by examining each individual circuits. Later, accounting the behaviors of two subcircuits collectively. Then now, we also introduce a small ripple approximation. What does it mean? Your ripple is very, very small, so that you can just ignore it. That is the concept of a small ripple approximation. The ripple component in the converter output is so small that the output voltage can be considered as a pure DC. Volt-second balance, the average value of the inductor voltage over one switching period should be 0. And M-second balance, the average value of the capacitor current over one switching period should be also 0. Then with these techniques, you can analyze a buck converter, even boost or any kinds of converter in steady state. Okay, let's examine the buck converter in steady state. If the switch is turned on, you can draw this equivalent circuit. When the switch is turned off, this equivalent circuit can be drawn. Then, this is the Q, is the switching signal for DTS. DTS is turned on. For a lesser period, then it turns off. Then what about this? When your switch is turned on, what about your inductor voltage? Here, this is turns on. This case, inductor voltage is what? Vs minus VO, right? This point is VO. This point is Vs. So your inductor voltage is Vs minus VO, right? Then what about this case? This case, when switch turns off, this minus point connected to the VO, the positive. This positive connected to the negative of the VO, right? It means, at this case, your inductor voltage is minus VO, right? At the steady state, the extent of these two rectangles should be the same, right? By doing so, you can fulfill the volt-second balance. Then this is a simple inductor current waveform. And this is average inductor current value. The average inductor current value was same with the average output voltage, right? So IL, that is a capital letter, then it means also average, right? DC component. So IL is VO over R. And that IL, that is the ripple component. Ripple component was simply calculated as like this. From what? From this the figure, right? Then your maximum inductor current is IL plus 1 over 2 del IL, because the definition of del IL is like this. So maximum is like this, and your minimum is written as IL minus 1 over 2 del IL. Then what about guess it. What is the current? Which current? What's that? That is the current passed through the switch, right? So when switch is turns on, the inductor current pass is connected to this switch. So your switch takes the inductor current. When switch turns off, diode takes your inductor current, right? Then what about this? This is the ripple current passed through the capacitor. But its average value should be 0 ampere, right? At the steady state. Then BAC is the output voltage ripple. Output voltage ripple is simply an integration of the capacitor current with 1 over C. So this is some very useful analysis and useful equations for DC converter. I mean the buck converter. Okay, so let's simulate this circuit and confirm the BO, PL max, PL min, and average IL. I mean the DC component of IL and delta IL, and IL maximum and IL minimum. Okay, then let's try to estimate the output voltage ripple. Okay, here the BAC is only consider the AC component of the capacitor voltage. Then this is the inductor current. The inductor current ripple is defined as like that and called del IL. Then I told you this ripple component, all ripple component flow through the capacitor, right? So this is exactly the same with the capacitor current. Then your capacitor voltage VAC is what? Integration of your capacitor current with 1 over C. Okay. Then the ripple component can be simply calculated as like that. For if you consider this point and this point as T1 and T2, then the ripple component is 1 over C integration from T1 to T2 with IC. Like this. That is just half of the switching period. Half of the switching periods. Then we know that integration of a waveform means the extent of this the triangular. Then you can simply apply the formula to calculate the extent of the triangular. So you have 1 over 2. Then what is your x? Is Ts over 2. And what is your y? Is del IL over 2. So you put this here, and 1 over 2 from the extent of the triangular. Then at the time, your IL was what? VO over L, 1 minus D, Ts. Then you can generalize del BAC as like this. This is a general expression of your BAC ripple component. So if you can in fact calculate the ripple component with this formula, or the ripple component through the frequency domain analysis. That's what we did in the beginning of this slide. It was 7.76 millivolt, and your simulation, it depends on your simulation tool, but it's 7.95 millivolt in this textbook. In fact, there's some difference, some error, but the error is not very significant. So you can just use it. What about in practice? In practice, we just use this. Many cases we use this formula. Many cases. By the way, we have some barrier. What kinds of barrier? Although we know the formula to get the ripple component, in fact, we have in practice RC, that is ESR, equivalent series resistor. So, if you have the ESR, then most of your voltage analysis technique you have performed is useless. Your voltage ripple is mainly determined by RC. Okay, think about it. Your VC ripple component consists of BAC, that is capacitor ripple, and also BESR. Sum of these two terms are the entire VC ripple. Then, if you calculate this, and this is the integration of capacitor current. But this BESR is what? Just RC multiply capacitor current. In many cases, this component is much larger than this component. Like this. In fact, that is so many cases this is much larger than this. So you can simply ignore this component. But still, it is meaningful to calculate the ripple component through the formula. The reason is that if you have, for example, very good capacitor, the very expanse capacitor, then ESR is low, usually low. In the case, BAC can be larger than BESR. So it is very difficult in power electronics. The reason is that we don't have, the right solution. We have optimized the solution. But even you find the optimized solution, as technologies are getting better, then your optimized solution is no longer work. So that's why power electronics engineers have many jobs or many opportunities. But it's very hard. Okay, now let's simulate this circuit with the ESR of 0.05 ohm. So, in your power electronics circuit, basically you perform the CCM-based formulas. But in reality, you always see the discontinuous the conduction mode. Why? Think about it. If your converter operated under no load condition, then you don't have any load. Then your inductor current should always see the discontinuous mode. It means in practice, even if you try to regulate with the CCM-based controller, in fact, it does not very well fit with the DCM operation. 어려워요, 그래서. 무부하는 항상 보잖아, 우리가. 부하가 없는 경우. 부하가 없는데도 내가 전압을 유지하고 있어줘야 되죠. 그럼 제어가 잘 안 돼, 오히려. 그럴 때가 훨씬 제어가 잘 안 돼. CCM은 이제 많은 경우는 CCM으로 동작을 하게 만들어줘요. 많은 경우. 그런데 부하가 감소하게 되면 이제 DCM으로 쉽게 들어간다. 그럼 그걸 어떻게 풀어야 돼? 도대체 내가 맞는 듀티를 어떻게 구할 수 있어요? 그걸 하려면 여러분이 2차 방정식을 풀어야 돼. 그러면 아까 얘기했듯이 4V에서 어느 정도의 듀티 사이클이 필요한지를 정확히 계산할 수가 있어요. 자, 그런데 여러분들 2차 방정식 푸는 거 쉽지 않지? 다 도움을 받아야 되잖아. 컴퓨터도 마찬가지야. 근데 컴퓨터는 이제 마이크로 프로세서 같은 경우도 그걸 하려면 다 수치 해석적인 방법을 써요. 수치 해석적인, 뉴턴 랩슨을 돌린다든지 이런 식으로. 근데 그렇게 하면 너무 느려. 그렇기 때문에 이 디스컨티뉴어스 컨덕션 모드에서도 잘 동작하는 제어 구조가 필요합니다. 그래서 CCM 모드의 제어기, DCM 모드의 제어기 따로 나서 이거를 구분하는 방법도 있고요. 아니면 퍼포먼스를 어느 한쪽에 좀 치우치게 맞춰 놓는 거야. 그러면 DCM으로 들어갔을 때 퍼포먼스가 좀 열세지만 큰 문제 없이 우리가 적용할 수도 있겠다. 이런 것도 있고요. 혹은 두 개를 다 아우를 수 있는 하이브리드 타입의 컨트롤러를 설계를 하기도 하고. 그 얘기는 뭐냐면 여러분들이 배운 그냥 단순한 PI 제어기 혹은 PID 제어기로 이 모든 게 커버가 안 돼. 고성능을 내기 위해서는. 자, 그에 관한 얘기는 다음 시간에 하도록 합시다. 수고했어요.